Well, thank you very much for the invitation to speak at this event, and it's really nice to finally have this event after two unsuccessful attempts. I want to talk about fire. Talk quite a bit about fire impacts to water. It's something that we spend a lot of time thinking about and researching. And in particular, we've been working in the southwestern Rockies of Alberta on a project, Southern Rockies Watershed Project. And what we've definitely seen is we're seeing some common elements in terms of those impacts on water to what's been observed in other fire affected regions in along the Rocky Mountain chain, but also quite a few differences. And so my colleagues from the U.S. Geological Survey, particularly in Colorado, often give us a hard time about the name of our project, Southern Rockies Watershed Project. And I remind them that for us, the Southwest Alberta, it's the deep, deep South. Because of course they're looking at that through the lens of, how is water in the Rocky Mountain chain affected, and really thinking about what does that look like in that Colorado region, in Arizona, in New Mexico, and so really the topic that I want to talk about today is, across that Rocky Mountain region, how much can we generalize those effects? Certainly many of the processes are the same, but the hydroclimatic setting is different. And really, so the talk today is primarily focused on what are the dominant controls that seem to be driving the responses that we see. And you're going to hear from a particular perspective from that part of the world, but I'll try to put it in context of the larger sort of the larger sphere of interest, I guess, of the Crown Managers Partnership. The other thing you'll notice is a very large list of co-authors here. And really this has been a very large project, and it's involved researchers from across Canada, the UK, now some of those researchers have moved on to the United States. So there's a large number of people that have contributed to this work. And so I'm going to be trying to provide a much broader kind of perspective on this. So this broader question of impacts to water, given our more contemporary experience with wildfire, particularly in the West. Most of you have probably seen on the news or in the media, the television, what some of those impacts are after fire. Here's just a couple of screenshots of newspaper pieces or web pieces. After fires, we see a shift in how runoff is generated, and that can result in some settings in some fairly catastrophic effects. So in some cases, there's concerns about flooding, certainly concerns about debris flows. And so I think it really colors the perspective of a lot of people thinking about, well, what happens to water after fire? And so lots of focus on ash, fire debris, flooding, issues of what I would call emergency sediment. So debris flows where people are actually injured or killed. And so those kinds of effects, well, they make for interesting viewing on the news because they are so catastrophic. Those effects tend to be comparatively short-lived compared to some of the other effects that we've certainly seen over the last 2 decades now, almost 2 decades. So I'm going to be talking about research that we've done in the Crown of the Continent, principally on 2 wildfires, the 2003 Lost Creek wildfire and the Crow's Nest Pass. And we studied the effects of that fire on water for over 10 years, for 11 years, from 2004 to 2014. More recently, we've done work on a nearby fire, the Keno Mountain Fire. As the crow flies, only about 55 kilometers or so, say 30 miles as the crow flies. Same basic hydrogeologic climatic sort of setting. Both severe fires, Keno probably a little bit more severe than Lost Creek, but both certainly at the upper end. But we've also have been studying other fires. When we began going down this road, I certainly never imagined that I'd be studying wildfire impacts on water as a good part of my career. But the fires just kept happening around us, and we just kept being drawn into studying some of these fires. More recently, after the Fort McMurray fire, the 2016 Horse River fire, we've done a fair bit of work on that particular fire, but it's in a very different hydroclimatic setting, a boreal setting. And then there's a number of other fires that we have been involved in capturing smaller data sets from. And so today I'm going to mostly focus on the longer term data set coming out of the 2003 Lost Creek wildfire, but commenting on some of the things we've been seeing after the Keno Mountain fire. And so really when we started down this road, it was at a time when wildfire water researchers were really starting to study this issue across the fire affected regions of the world, Australia, the US, parts of Southern Europe. And so a lot of this time was spent really trying to get a handle on what is the full breadth of the scope of impacts of these fires to water? How big are those effects? And then some of those questions of sort of resilience, how long do those effects last? And so that really was a lot of the focus of the initial work. And I'd mentioned we have a fairly large research team. And that team really has focused on this disturbance from a number of different perspectives. How are these wildfires affecting, some of the fundamental hydrologic drivers in the headwaters? How do those in turn affect water quality and in turn stream health? But then other groups of researchers are looking at, well, what do those effects look like downstream at increasingly larger basin scales? How do those effects propagate downstream? And then looking at what are some of the broader implications of some of those impacts on drinking water in particular, and some of the ecosystem goods and service, the economic implications. Today, I'm going to focus primarily on simply those headwaters effects, looking a little bit at the hydrology, the water quality, and some of the connections with stream health. And I want to look at this through the lens of again, sort of resistance and resilience, and thinking about impacts from a broader perspective, going, well, okay, we can have some attributes of water that are affected really quite severely, but those effects diminish quite rapidly. So we might have some kind of a trajectory of recovery that we see fairly rapid recovery. We might have other values associated with water that recover much, much more slowly, perhaps coincident with sort of recovery of vegetation. In fact, there might be issues, water values, where we see little or no effect from wildfire on those. Or we might have other sort of parameters where we see effects that are actually delayed in time. And so the initial effects don't show themselves, but a little bit later we see some of those effects. And so I want to use this as kind of a springboard to comment on a few of those things. I'd mentioned we've been working a fair bit with some of our American colleagues, and in particular colleagues from the US Geological Survey. Back in 2013, there was a really good workshop organized, AGU Chapman Conference, on wildfire water response domains. And we brought together researchers from all over the world. This is a nice piece that was written by John Moody and Deb Martin, Sue Cannon, others, kind of looking at this issue from a Central Rockies perspective, and really trying to think about what are the primary controls. And from that perspective, it was in that part of the world, it was rainfall-driven hydrologic processes that are connected to fire effects on infiltration, erosion, generation of runoff. But the broader perspective here, bringing together people from all over the world, we spent a lot of time, we spent over a week throwing chalk brushes at one another, trying to figure out, well, why do we see these different response regimes that really reflect the integration between the precipitation regime, the geology, the physiography, all of those issues. And so here, what I'm going to talk to you about here, you would consider, I think many of you, the Northern Rockies. We got a very, very strongly driven snowmelt driven hydrology, very high precipitation in that part of the world, 700 to close to 2,000 millimeters precipitation, very, very high runoff. And in particular, the stream flow regime is really dominated by a very large contribution from groundwater sources. And that becomes really, really important, So jumping forward then, looking at some of those hydrologic effects, building on some of the points that Vita talked about, what we see certainly after a fire in that particular part of the world, very large impacts on snowpacks. So very, very obvious after these fires, you lose the crown, you then reduce the interception losses of snowpack interception, and so you end up with more snow on the ground. So we studied this fire for over a decade, and so annual snowpack surveys here, you're looking at mean snow water equivalent in the reference watersheds in green, the burned watersheds in black. And you can see the snowpack water equivalent is substantially higher after fire. And so we continued that for over a decade, and got the range of low snowpack years, high snowpack years, but consistently those effects remain high. Similarly, that same interception effect affects net precipitation from rainstorms in the summertime. So some of that canopy would be intercepting rainfall and evaporating it back to the atmosphere. But after fire, you lose that canopy, and so you get greater net precipitation. And so in the terms of, this is now looking over a decade, the average over that long period of time, we had almost an 80% increase in mean snowpack water equivalent after the Lost Creek fire, with about a 36% average increase in the net rainfall. And so you put those two together, that's the total effect of the fire on precipitation. It's just over 50% increase in total precipitation. And so that's a massive amount of additional net precipitation that's forcing the hydrologic behavior of these landscapes. Lots of concern about fire effects on flow, and in particular peak flows and storm flows that might potentially lead to flooding. And so over that long period of time, we have a very long hydrometric record, really then just looking very closely at the peak flows, the storm flows themselves. You can look at a storm hydrograph and doing a simple base flow separation, you can separate out the fraction of that storm flow, or fraction of that flow that would have resulted from the precipitation event. And doing that over time, and this is now, again, just over 10 years of data, looking at peak flows, the one thing, and this is in quite stark contrast to what has been seen in other parts of the Rocky Mountain region, is yes, as precipitation, as our storm event sizes go up, we see a dramatic increase in those storm flows, but very little, if any, demonstrable effect of the fire on the routing of those flows. So in this particular setting, we saw no impact on peak flows or flood flows as a consequence. In contrast, it's not that we didn't see hydrologic effects, we certainly did. Here you're looking at long-term average flows, and it's broken up into sort of 2-week periods. This upper graph is the difference in water production between burned and unburned landscapes. And so you can see early in the season here, near the beginning, the onset of the melt period, we start to see those burned landscapes producing much more snowmelt runoff. But then that starts to diminish back down to sort of baseline. And in fact, when we start to get into the early to midsummer period, we may even have a slight decrease in the flow generated from those burnt landscapes. So effectively what's happening is the hydrographs look like they've been shifted forward. And so this bottom graph here, you're looking at the absolute weekly flows. Again, green is the reference watersheds, black is the burned watersheds, and it's a fairly large collection of burned and reference watersheds. And so you can see that really the dominant effect of that fire is in advancing the timing of the melt, the onset of the melt runoff, with potentially some small decrease in those summer flows. So the big picture, you take the jet up to whatever, 50,000 feet, looking at that particular part of the world, we saw really, really strong resistance to disturbance effects on peak flows in particular. Here, this is an example shortly after the Lost Creek fire. Here's the Lost Creek fire polygon. It actually burned around a previous wildfire, the Gorge Creek fire. So this burned about 3 years earlier than Lost Creek. And it wasn't very long after the Lost Creek fire. This is the Gorge Creek fire. And basically, you know, you had slow recruitment of deadfall riparian wood that was moving into these stream channels. And it took a fairly large event early after the Lost Creek fire to move all of that wood down into the channel. We saw the same thing after the Lost Creek fire, after the 2013 floods. And so I think this is a really good example of one of these potential responses that might actually be delayed in time. While you might have recruitment of coarse woody material into these stream beds gradually over time, it takes large hydrologic events to actually move that material. And in that sense, hydrology is very, very similar to wildfire science in the sense where you might have you might have only 1% of your fires burn, 99% of your burn area. Well, it's the same thing hydrologically. It's a very small fraction of the time when most of those effects are generated. Here, jumping into some of the water quality things we saw here, looking at physical water quality, stream temperature in particular. You might imagine that after a wildfire, you lose the canopy, you lose the riparian shade, that you'd expect to see fairly large increases in stream water temperature. In that part of the world, though, these are sort of our temperature traces for many, many years in our unburned and in our burn systems. And it turns out in that part of the world, the effect on stream water temperature has been really, really minimal, from maybe 0.5 degree to 2 degrees on average, maybe 1 to 3 degrees in terms of maximum annual peak summertime temperature. And the dominant reason for that is in that part of the world, stream temperature is dominantly governed by the fraction of groundwater that's contributing to that stream flow. So groundwater is cold. It takes on the background temperature of sort of the mean annual temperature of the region. And so that groundwater is really, really cold in the summertime. It's actually really, really hot in the wintertime during the dead of the winter. And so in that part of the world, of the Rocky Mountains, the stream thermal regimes seem to be under groundwater or hydrogeologic control rather than radiation control. And as a result of that, we really saw little, if any, effect of the wildfire on stream thermal regimes. By contrast, however, we did see fairly large effects on water quality, as you can imagine. And we have studied a very broad range, full suite water quality. I'm just going to touch on a couple of things. Here on this bottom graph, you're looking at an 11-year record, and it's just, these are kind of annual roll-ups. There's a lot going on inside there, and here you're just looking at total nitrogen. But total nitrogen is a really good example of one of these parameters that the impacts start quite high and then recovered fairly quickly. And when I say recovered fairly quickly, so we've got the burn watersheds, the reference watersheds, and then salvage log watersheds in orange. And you can see after that fire, the recovery is fairly quick. And quick from an ecological standpoint, 5-6 years back to baseline. In contrast, other direction. In contrast, we saw other things with other kinds of water quality parameters. So here we're looking at sediment production, again on an annual time step, and then phosphorus production. So sediment and phosphorus is actually really closely associated with sediment as well. So phosphorus is a key nutrient that's driving stream ecology in these systems. And it looks like after the fire, you might have seen some early signs of recovery. But in fact, if we window out, all we saw was basically kind of a wet year, a wetter year, drier year, drier year. So really what we saw was dominantly the influence of climate from year to year to year. Wet years, dry years, years with large events, years with small events. And when we windowed out to looking at this over a decade, those fire effects were persistent and lasted for an awful long time. In 2013, we had a very large channel modifying flood event in that part of the world. And the only thing that changed there was our reference watersheds lost their mind that year. And so we see those effects basically persisting over a very, very long period of time. And in particular, phosphorus is an important one as we kind of look at, stream health, because in that part of the world, phosphorus is the dominating limiting nutrient for ecosystem productivity. The line there is 30 micrograms per liter, which is pretty much the switch from oligotrophic or limited systems to eutrophic systems. And here when we're talking about Rocky Mountains, we're talking about really, really nutrient poor systems. So a small amount of additional phosphorus can have a very large effect. And here's where I want to sort of jump sideways a little bit, thinking about why do we see things that are similar or different from other parts of the world. Here, if we look at, and sorry, I don't have this parallel data for on the American side, but here we're looking at the dominant bedrock geology. And I've just broken this up into really simple groups: sedimentary geology in pink, and then metamorphic, igneous, intrusive, extrusive, metamorphic. And what you can see in the part of the world we're working, this is all dominantly sedimentary. So limestones, siltstones, mudstones, marine shales, fine bedrock that breaks down into fine particulate matter. And that's really quite different than we see in landscapes that are dominated by igneous or metamorphic bedrock, where those primary materials weather to much coarser materials. The other thing that's different here is we also have 100,000 years of glaciation in 4 major events. And so there's a really poor coupling between the superficial geology in that part of the world to the bedrock geology. And that sets us apart from Colorado, where you're looking at really disintegrating, weathering granitic bedrock from systems with fundamentally different bedrock geology and glacial history. And really that becomes really important, because it really means that in our part of the world, fine grained sediments really dominate what happens. And it turns out that those fine grained sediments are really, really critical for the transport and long-term storage of some of those contaminants. And it's really tied into the longevity of a lot of the things that we see here. So in that work, after the Lost Creek fire, we saw those effects on sediment, and contaminants associated with sediment last for well over a decade. And that really sets that response domain apart from most other regions of North American Rocky Mountains, and certainly Australia, Europe, and many other places. So we go a little bit further east, 2017, 2018. I think this is after the 2017 Elephant Hill fire. Now moving into the West Kootenays, out of the East Kootenays, we start to pick up a different geology. And so here you can see the jade deposits on the hillside. There, after the Elephant Hill fire, this is with the BC Forest Service. We certainly saw some of these debris flows and mud flows that are characteristic of some of those response domains further south. But these are things we have not seen on our side of the pile of rocks. Taking a look at nitrogen just a little bit more closely, again, it looks like you have complete recovery here, but let's zoom in here a little bit. We've been monitoring water quality at really high temporal resolutions. Here you're looking at the reference watersheds, and this is nitrate, which is really highly mobile. And you can see that nitrate basically pulses on a seasonal basis, and it actually hits its minimum after the peak of the melt freshet, so midsummer. And so there's a really tight correlation with stream nitrate, export of stream nitrate, and what's going on with nitrogen consumption on the landscape. Here, looking at the burn landscapes, you see the same seasonal pulsing. The two lines here are basically the upper and lower quartiles for the reference watersheds. And you can see over time, the burn landscapes, the nitrate concentration dropped back to baseline, but then started to go below baseline. And in particular, in the salvage log watersheds, those nitrate concentrations went well below the baseline in the unburned. And so here, looking at the medians, this is looking at sort of 3-year time steps after the fire. So you can see the reference watersheds are pretty stable. The burned watersheds get back to baseline after about 6 years, but then stop to drop below baseline. And in the salvage log watersheds in particular, they have now dropped well below the reference watersheds. And part of what's going on here, as far as we can tell, is after the salvage logging, because of the additional ground disturbance imposed with the salvage logging, lodgepole pine in particular needs mineral soil for the seeds to germinate. And so we had tremendous recruitment of lodgepole pine in the salvage logged areas. Here, looking 10 years later, really vigorous stand growth in the salvage logged areas. And that's in stark contrast to what we see in some of the upper montane or subalpine transitions, where our vegetation recovery has been exceedingly poor after that fire. And we think that's sort of tied in. Let's see, where are we? I'm gonna speed up here a little bit. Part of the driver here then is this issue of sediment and its association with phosphorus. And without getting into the detail here, phosphorus is really closely tied into sediment. It's not just that we get more sediment and more phosphorus, but the bioavailability of that phosphorus is higher. So, you know, from a conceptual model, you can have sediment that's phosphorus bearing that's put into a creek, and that phosphorus is going to exchange with what's in the water column. It's going to settle on the stream bed, and so you're getting aqueous exchange between the solid fraction and the aqueous fraction, which really is driving a lot of those ecological effects. And so, not really surprisingly, after those fires, we saw a little bit of extra phosphorus that produced a massive increase in algal productivity, anywhere from about 10 to 50 times greater algal productivity, depending on what measure of algal productivity that we're talking about. And oops, I'll go this way. And as a consequence, you've got more algae in these systems. Well, that's food. As part of the base of the food chain. So it was not surprising that we saw the macroinvertebrate communities respond fairly quickly, a fairly dramatic increase in abundance, a shift in species composition. It's not that we necessarily lost species, but we certainly gained a lot of more mesotropic species, true flies, diptera. And the point here is looking at the macroinvertebrate community. This is 10 years after that fire. The persistence of the legacy effects on those macroinvertebrate communities has been maintained for almost a decade. And then, not surprisingly, you've got more algae, you've got more invertebrates. Well, that's food for some of the higher predators. And so we saw an increase in growth rate of cutthroat trout, rainbow trout in those particular systems. So the system it's a fairly simple story. It's a classic sort of bottom-up trophic cascade where the fire produced an increase in sediment, which produced an increase in phosphorus and then more bioavailable phosphorus, which in turn drove increases in aquatic ecosystem productivity at a number of rungs on the trophic ladder. And as I'd indicated, many of those impacts have lasted now for an exceedingly long period of time. Jumping, and I'll try to wrap this up so there's a little bit of time for some questions to what we're seeing after the Keno fire. Well, a lot of this has been deja vu, but not all of it. So we've seen many of those same kind of effects, even though these fires are fairly close and the hydroclimatic setting, the geologic setting is fairly close. We're also seeing some notable differences. So here, just a snapshot. Last year was the 3rd year after that fire. So here, if we're looking at the first 3 years after the fire, what did we see after the Keno Mountain fire and Lost Creek, and how did they kind of compare? If we look at total nitrogen, well, the absolute amounts are somewhat variable. These numbers here is how many times greater the nitrogen production in this case after the fire is compared to the reference. And you can see the effect of those two fires on nitrogen production is pretty similar. The absolute amount of sediment that we're seeing out of the Keno Mountain fire is quite a bit higher, but the relative amount and the relative impact of the fire is again not too different. We are seeing some subtle differences in phosphorus, and those in turn are driving some interesting differences in aquatic ecosystem processes. And probably one of the things that's most notably different, and we're still doing a lot of head scratching about this, is out of the Keno Mountain fire, we're seeing far, far less carbon coming out of those, and some of the other contaminants, metals like mercury. And so while there is a lot of similarities, there's also a lot of interesting and important differences. And so here, I want to caution you at not interpreting this with too much resolution. Again, thinking about what we saw after the Lost Creek fire, that variability from year to year to year was driven far more by variability in weather from year to year than it was by any ecosystem recovery. So at this stage, I would not try to overinterpret what we're seeing in these two fires too much. So really, just to wrap this up, then, largely we are seeing similar mechanisms and processes that are governing those responses across the Rocky Mountain regions, but different processes really dominate the responses in those different regions. So the effects that you see in one of those regions that might dominate the impacts on water, they might not be so important in another particular region. And so basically the comment sort of to leave you with is caution against broadly generalizing the scope of some of those fire effects on water. Lastly, sorry, because I know some people were interested in some of the literature. So here's some of the pieces that we cited, and Natalie has got this. So if you're interested, she can pass that on to you. So thank you for the invitation. And if there's any, I guess I'm actually right out of time. So hopefully there's time for questions afterwards.
Thank you very much, Uldis. We do have a few minutes for questions because we did lose a speaker today, so we're okay to dip into time a little bit here. And we have two questions in the chat box, but while I'm asking these to you, others can add additional questions to the chat box or raise their hand, and we'll allow you to ask the questions yourself. So again, thanks for that great presentation. Our first question is from Mike Munoz, who says, awesome work. The Lost Creek fire researched appears to be a first entry or initial fire event. Have you had opportunity to look at similar effects in terms of the reoccurrence or reburn, like second and third entry fires of initial fires and resulting disturbance?
Okay, no, it's an excellent question. We have not, but that said, while we have not looked at reburns, we looked at something that's somewhat parallel in concept. Because we studied the Lost Creek fires for so long, not just burned landscapes, but burn and salvage landscapes. And then we had a very, very major catastrophic flooding event that occurred in 2013, almost a decade after the fire. What we had the opportunity is to look at intersecting climate disturbances, both individual disturbances, some anthropogenic disturbances, if we think about salvage logging as a compound effect, but then the impact of, say, severe flooding on an already burned landscape. So it's not exactly what was asked, but it's really quite an interesting story. So we can see even a decade after wildfire, when that flood occurred, the flooding magnified, one, it reactivated some of the fire impacts and the salvage logging impacts, and really dramatically showed some of those compound climate-driven effects. And that's a piece that we're in the final stages of a revision for publication. So hopefully you see that one in the literature in the next few months.
Great, thank you. Our next question is from Eleanor Bassett, and she asks, any connections to livestock use in these areas or wildlife and ungulates to the level of nitrogen and phosphorus? Also, would these levels be considered safe for drinking water for livestock?
I have to beg some limited familiarity with water quality standards for livestock, and certainly I'm familiar with some of those sulfur or sulfates, and calcium becomes really important pieces. And honestly, we did not see much in terms of the sulfate and calcium signatures. However, we certainly saw a lot going on with nitrates. Nitrogen in general, nitrate in particular. And so back to that question in terms of stock water, I can't really say much meaningful about that. From a drinking water standpoint, we have certainly done an awful lot of work on potential impacts to drinking water treatment and treatability. And certainly wildfires definitely impose some significant challenges to treatment of drinking water. It's not that that water cannot be treated, but it imposes fairly substantial, under the right conditions, can impose a fairly substantial operational burden on producing safe drinking water. So it's not that drinking water is necessarily threatened, drinking water security is threatened, but certainly the costs for producing that water can certainly go up.
Great, thank you, Uldis. Our next question is from Brooke Capella, and she asks, you said that there was a mean stream temperature increase, but little meaningful effect from the fire at Lost Creek. Could you discuss this a bit more? What caused
sure.
temperature increases?
Yeah, so it's not that, if you think of the thermal regime of rivers, it's going to be a combination of drivers: air temperature, radiation control, riparian shade, those kinds of things. So after the fire, we certainly lost the riparian shade. But what was interesting in the systems that we're studying, the thermal regime is under such strong control by the hydrogeology that even a loss of that riparian shade produced, while it did produce a detectable increase, that increase was really, really small. As I said, it was anywhere from 0.5 degree to upwards of 2 degrees, which is probably biologically not particularly meaningful. Even if we're talking about peak summertime water temperatures, at a very upper end, it was about 3 degrees in terms of a fire effect. And so that is not enough to drive subsequent changes in dissolved oxygen concentrations or those kinds of things in receiving streams. That said, I also need to be cautious that while that's what we saw in these headwaters that are really groundwater dominated headwater systems, you do not have to go down gradient very much further to see that groundwater influence drop off fairly sharply. And under those situations, radiation, air temperature and radiation control and riparian shade are key governing factors. So what we saw was kind of an oddity that really reflects that particular hydroclimatic setting in these upper end Rocky Mountain headwaters, if that makes any sense.
Great, thank you, Uldis. Maybe we'll do one more question and then give you a break, give you a chance to have a drink of water and move on here. But I will mention there are other questions in the chat box, and from both our participants who are asking questions and for Uldis, the fire forum that ends today is not the end of this discussion. And so we'll be able to communicate through email and otherwise and have exchange some more of this information. But to give Uldis one more question and then give him a break, Tyler Hoker asks, I'm a little confused about the relative magnitude of warming from the loss of canopy cover versus the changes in groundwater / surface water inputs. Could you clarify your thinking on that?
Okay, so sort of
can I interrupt really quick? This is Tyler. You covered that really nicely, Uldis. So
okay.
we can ask a different one because it was a very similar question to Brooks.
Okay.
Great, thanks. All right, we'll move on and we'll get a question from Elisa Wade really in here quick. Another clarification question. Can you restate reasoning behind different levels of post-fire recruitment in burned versus salvaged?
Vegetation recruitment, presumably. Is that what?
Yes.
Just to clarify. Yeah, okay. What we did see, particularly in the subalpine transition, you get up into the alpine, there wasn't a lot of fuel up there, but really the systems we studied were upper montane up through subalpine transition. So largely pure lodgepole pine dominated up through Engelmann, spruce, subalpine fir kind of complexes. And in the upper montane positions, particularly those that were salvage logged, what we saw, you've got two disturbances layered on top of one another. You've got the fire disturbance that presumably exposes some mineral soil, but then the logging disturbance, the salvage logging disturbance further exposes greater mineral soil. It also breaks the slash down. And so what we saw was really, really vigorous recruitment after the salvage logging was completed. We had well over 100,000 stems per hectare in terms of small seedlings. And of course, they self-thin quite well. But what that's meant in the salvage logged part of the landscapes, we saw very, very high stocking. And because pine self-thins quite well in that system, it's really led to really lush growth and post-fire regeneration in the salvage log pieces. By contrast, in those subalpine transitions that burn very, very hot, you can walk through there, and the grass is still whatever, mid thigh deep. You'll walk through there and you have a hard time finding seedlings. They're still buried beneath the grass, but you're lucky if you can find a spruce seedling or a fir seedling every 50 to 100 yards. And so the recruitment in that particular subalpine transition that burned very, very severely is dramatically different than we saw in the upper montane, particularly where it was salvage logged. So the salvage logging in that particular instance, while it contributed to a lot of water quality deterioration, paradoxically, what it did is it seemed to drive some longer term, more rapid recovery of nitrogen because of the dramatic recruitment and growth of pine in that system. I don't know if that clarifies the question that you had.
Well, thanks very much, Uldis. That was fantastic research and fantastic presentation. Please join me, everyone, in thanking Uldis for his great work.